Okay, so let's start the final lesson. Final. Okay. And this lesson, we will summarize all over the floor. And before studying your design, you have to consider many things before studying your design. And the first question is, what are you going to design? And why you are going to design? And there are many possibilities. You want to design the final commercial product, or you want to design a sample product, or you design check out if you can develop it into a product, or you may want to obtain the top data and submit to a conference, or you want to demonstrate a new function and submit it to a conference, or you design just a training for freshmen, or you design an only simulation and don't publish it. There are many stages. So you want to make sure which stage you are in. So when you design, sometimes you are told from your boss, hey, you design this. And sometimes when I was a student, I was often asked that design something, anything is okay, but there is a space, so you have to design something. It sometimes happens. And once you have experience, you say, please let me design this. You can ask your boss to let you design something. And in the end, you may say, what kind of design are we going to do? What makes me very interested? So there are many stages for what and why, and also you have many stages, the motivation, why you design. And after that, you will decide the specifications. What is the supply voltage? What is the operating frequency? And how many hours we can consume? And what is the non-performance? How many bits we have for AD or EA? Or what is the jitter for DLL? What is NF for LNA? We have to have non-performance. And also, we will suffer from PVT variations. So what kind of PVT variation is taken into consideration? We have to take all process corners. Is that 1 sigma or 3 sigmas? What is the supply voltage variation? It is plus minus 5% or plus minus 10%? Or what is the T variations? It is from 0 to 80 degree or minus 25 to plus 125. So what kind of PVT variations should be taken into consideration? We have to decide this before studying the design. And also, you have to decide which process technology you use. You will use TSMC, UMC, or you might ask VDEC, or you don't know. But anyway, you will decide a process technology and when is the deadline. From tomorrow, maybe impossible. On 1 month, it's difficult. 3 months, maybe easier. And in order to decide the process and deadlines, we have to have the performance and cost. And of course, 28 nanometer process has high performance compared with 118 nanometer technologies, but it's very expensive. So we have a trade-off between performance and cost, and we have to consider the trade-off between performance and cost. It might not be your work, it might be your manager's work, but you have to consider it with your manager. And when is the deadline? The fastest schedule, anyway, after you finish your design, you will submit it immediately. Or we have a shuttle schedule. So for example, all ICQFT and another Vietnamese university, they may have the same shuttle. So the shuttle schedule will be decided first. Or sometimes you may achieve by yourself and submit to TSMC. So your schedule is anyway as soon as possible. It depends on your project. Or you want to submit to ISSCC. So we have to submit this and we have to measure the device variables. Or suddenly your manager suddenly asks you to sign this. It sometimes happens. And which process we use. And we sometimes, some process provides only cadence tools, cadence technology files. And some process provides only synopsis files. And some technology we can choose for synopsis or TANA or third party. So sometimes I'm not familiar with cadence, this function. And this part I have to use mentor. So there is some many process, but only this process has mentor this. So we have to choose this process. It sometimes happens, but mainly decided by performance and cost. And for my case, shuttle schedule is always available. But it depends on your work. But before studying, you have to make sure what is kind of. And also, before studying the design, you have to consider how to measure your. And you will measure in package on wafer. You have to consider it, and based on how you measure, you will decide what kind of circuit you want to design. And when you assemble the package, what to do with board. And you can make your own board for your chip. Or in this case, this is my experiment that we designed this for another project, and we found that this board can be used for this project. So based on this board pin assignment, we will change the final pin assignment of our circuit. And also we want to make sure what kind of measurement device we will use. We will measure the chip by oscilloscope, or spectrum analyzer, or real-time oscilloscope, or sampling oscilloscope, or using network analyzer. We have to consider how to measure before starting your design. And also, if you don't have a measurement device, for example, if you want to design 100 gigahertz operation, but you don't have such kind of measurement system. Your measurement system can measure up to 20 gigahertz. And you don't want to give up to design 100 gigahertz. So in such case, you design kind of measurement model. and embed that measurement macro into it. So that you, by using that macro, you can confirm that the circuit itself operates in 100 gigahertz. And through this macro, you will measure this macro by 20 gigahertz oscillator. And you have to think of such kind of measurement macro and embed it. So in order to design this measurement macro, you have to consider how to measure it. And then now you decide what kind of circuit you measure and how to measure after fabrication. You will decide what kind of cathode tools you use. And we want to use a cathode tool that we are used to. And we don't want to move to a new cathode tools for that process. But some process, I'm used to synopsis, but this process provides all the cadence set of files. In such case, we have to learn how to use cadence. And so the process technology has priority, and we have to use cathode tools that the process provides. We cannot use what we want to use. We have to use the process, the cathode that the process provides. And sometimes we have to customize the set of files by yourself, as you want. And in most of cases, you design your circuit by a team. So when you design the circuit by your team, finally, all the data converge into one circuit. So at that stage, you will have many trouble. So in order to avoid the trouble, maybe you have to decide how before starting design. For example, you will use uppercase or lowercase for cell name and meaning. And maybe also designer 1 use inverter 1 and designer 2 use the same thing, inverter 1. When they merge, you have both. So I recommend that first, before starting your design, you decide the rule that the cell name should have your name. So in my case, my design is always T underscore inverter. TT means total. So A underscore inverter, or he will use T underscore something, and you will use A E underscore something. So before starting, you have to decide it before starting your design. And this design merge step, you will have very big trouble. Especially this uppercase and lowercase confusion is nightmare. And once you have mistakes when merged, your chip does not operate. And millions of dollars risk. And okay, now we decide what we design and we decide what kind of rule we have. And then you will have spice parameters first. And take a look at the spice parameter file, and you will see that what kind of model we use. We use low power MOS transistor or high performance MOS transistors. And sometimes, for example, high performance might be an option, and we have to pay additional fees to use high performance. In that case, your team has to decide this time we use only low power. And of course, all of you have to decide decide the same model and same transfer parameters. And also there's the libraries. This is typical, slow, and fast. And which library you use. That means what kind of corner conditions we have to take into consideration. And also we have to consider this is sigma or 3 sigmas. And the sigma and 3 sigma, it will make us very big difference. So this number is sigma or 3 sigma, and which we have to take care of 3 sigma or sigma. So these two are very important, especially when.
Can you explain more detail on the sigma or 3 sigma?
Sigma and 3 sigma means this is a random distribution. So randomness, variations. So for example, when we have, for example, 100 chips, and maybe the center is 10, and for the 20%, the on-site thickness is coming like this, and lower 20% is the thickness. When this is a sigma. When this is 3 sigma, top 0.3% has this thickness, and bottom 0.3% has this. So, and this depends on the process technology, it depends on the man who takes. There is physics. Once we have a process technology, the distributions are decided. And when he makes these files, if he thinks this should be sigma, they put sigma value. And if they think this should be 3 sigma value is in this one. And that is their side. And for our side, how many sigma we have to consider? We can throw away only 3%, or we can throw away 10%. And so, depending on the fail ratio that we want, we can relax, or we can have strict confinement, strict conditions for design. And once you have spice parameters, this is the first thing you have to do. You will draw the IDPD curve. And usually use L minimum and W equals 1 micron. And draw this IDPD curve. And from this IDPD curve, you can see the threshold voltage and also the flatness of here, so that you will see the maximum gain you can have on all ends. And from here you can see the ratio of NMOS and PMOS. And this graph gives you very big information. So especially when you use building design and analog circuit, you often come back to this graph to decide a bias function. So by using this graph, check threshold voltage, drain current, and flatness. And so this graph is often to be referred while you design a circuit. So print out this graph and put this graph on your desk. So in my desk, I put this graph for 0.18 and put this graph on 65 and put this graph on 28. And then we will decide a gate mix. And as I told you in lesson 1, we have wire capacitance. So the wider inverters have larger drain current, but the larger inverter has larger input capacitance. But assuming the wire capacitance is the same, the large W infinity the speed, forcing power here. And usually the standard W is L minimum times 5 to 10. And the PW is 2 or 2.5 times larger than the one of NMOS. And this number is very rough estimation. So besides the WP, this WP decision is very important. So first, L minimum and W1 micron curve is drawn like this. And maybe the 2 times W for B is drawn like this. And when WP is larger, this graph is getting larger and smaller, W is getting lower. And also you will see the inverter input output characteristic first. And you will draw this line. And large P will move to this side. And also you will run a transient simulation. This is the input and this is the output. And you will see the output curves like this. And larger WP will move like this one. And because this is a rising input and this is falling input, so the falling input is decided by NMOS. And falling input and rising input is always decided by PMOS. So the rising input performance will change if you change the WP. And from these 3 graphs, you will find the optimum P, such that the PMOS and NMOS have similar characteristics, as similar as possible. So as similar means usually the drain current wants to have the same. And this logical threshold is really, and rising and the falling time and rising time is the same. That is ideal. So we will adjust the size of PMOS in order to have these matched performance for NMOS and PMOS. And then you will take a look at the junction capacitance of transistors. There are many types of capacitance on transistors. So you have to estimate how much capacitance it has. And this is the PN junction capacitance and PN junction capacitance depend on the reverse bias voltage. And in the spice parameters, we can see that there is a parameter CJ, HDI, CJSW, CJK. So you pick up these values and calculate how much capacitance we have per unit width. So for myself, I usually say that per 1 micron W, how much gauge capacitance we have, and how much drain capacitance we have, and how much source capacitance we have per unit W. And we calculate this for both NMOS and for PMOS. So, and after knowing the transistor performance, first you design inverters. And of course you will do a hierarchical design inverter, make inverter single, and predict and connect and simulate and see the rate. And And then maybe this is a check if you have good kind of environment. So first, before doing into the detail of your circuit design, for example, if you design AD converter, before getting detail into the AD converters, but first you confirm that your CAD environment is correct, and you have to set up all the CAD environment first. So in order to set up that, you design first the chain of inverters, and then draw the layout, and you will see the design rule manual and confirm what kind of we have. And when you design a layout, you have to put all the data on grid. All the layout is must be, and you will check the minimum grid before starting your layout. And also you will check 55 dB wire is allowed or not. And again and again, off-grid means you are dead. Off-grid means you are dead. So all the data have to on-grid. And once you have off-grid, you are dead. You go back from zero and start the layout from the start. Off-grid means you are dead. And after you design inverter or NAND gate, you will check you will have a correct LVS and DLC. And in this case, you check LVS and you check DLC and intentionally put errors. Intentionally put errors and see how it's highlighted on the layout. So intentionally put some errors and see how the DLC error are highlighted, like here or and you have to decide the LVS options. Also, this should be decided before starting your design as a team. So your team have to have the same common LVS options. So march parallel, this and this are the same or not. You have to decide. And also how many mismatch is allowed. And also this kind of label connection, virtual connection is allowed or not. You have to decide. And what kind of filter do you use? And it depends on what kind of dummy transistors you have to have. And some technologies does not need any dummy transistors. And some technology have to have dummy transistors. And some technology asks you to all turn off the transistors. And some technologies, all the nodes should be ground. It depends on the technology and it depends on your team. And actually, it depends on the technology that how to apply these dummy transistors. And your team has to decide what kind of filter to use. So, I have many experience to design many teams, and some teams have to put all dummy transistor on schematic. And some teams, they remove all the dummy transistor on schematic. So it depends on your team. And recognize gates, it's also an option. So again, in this case, inverter for NMOS in one is close to the source. And this schematic N1 is close to drain. So, but both of them are NAND gates. So, if this layout is allowed or not. And it is, of course, it depends on your team. And I recommend you to don't recognize it. It is my recommendation. I always use don't recognize it. That means this and this is error. This is my recommendation. But of course it depends on your team. If your team are allowed, you can use it. And another LVS option, case sensitivity. And this is very, very, very important. The case sensitivity is allowed. And I recommend you to case sensitivity on. Case sensitivity on, I recommend you, and this is error. I recommend. But of course, this is depend on your team. So your team will decide before starting your design. And after you run LVS DLC, you will have RC instructions. And RC instructions, again, all the wire come with resistance and capacitance, and sometimes inductance. And in this case, the capacitance are attached to the wire, all the wires. So in this case, let's say input and output characteristics. Without LC, we will have this kind of curve, but after LC introduction, we will have this kind of curve. And again, after the layout, LC introduction, after LC introduction means you are on a very final stage. And your deadline might be tomorrow. So once you have this kind of performance change, you will have 90 days. So you adjust HDIS parameters. You adjust HDIS parameters before starting your design. You adjust HDIS parameters and prevent this before and after LC introduction performance or diverge. And actually, before starting your design, you do the schematic and layout and instruction, LVS DLC and instruction, and adjust HDIF key. And this is the main reason to start to go until RC introduction first. And in this stage, you find optimal HDI parameter, and then you start your design using this parameter. And actually, this is the main reason that we have to do layout first. And inverter are okay, but for my case, in my experience, flip-flops are the best to find these HDI parameters. So I often design inverter, the flip-flops plus inverter, and make dividers, and compare the maximum frequency of inverters, and we decide HDI. Okay, and after that, you decide power and ground. And you have to decide how many power blocks we have. You divide a power supply for analog, and power supply for core, and power supply for I/O. And I wonder power supply for RF and power supply for AE controller, power supply for VLL. You have to decide how fine you will divide the power supply. And also you have to decide deep and well. You can use deep and well or not. And if you use deep and well, how to divide it? You use deep NL for all analog blocks, or only these analog blocks are used deep NL. You might use deep NL for audio buffers, or you might use deep NL for digital side. You have to decide it. And how many pins you have. And the wire comes with, for power supply, the wire comes with R. So we want to use as many pins as possible for power. And for Intel processors, half of chips are assigned for power. And how much current density we have. And consistency for multi-designer projects. So again, you have to decide what kind of naming rule of yourself. And other things we have to consider is input and output pins. What kind of input pins we have and what kind of output pins we have. And from the external pin, that means we input the signal from external devices. For external pins, what is the frequency of the pin? And after deciding the frequency, you have to decide the termination, the match, termination impedance is embedded on the chip or put 50 ohm resistance on PCB. Or that is analog signal or digital signals, or that is I/O buffers. You have to decide it. And also or after deciding the input and output pins, and I strongly recommend you will have insurance signals. And this might be the first time to see this name, insurance signal. I give this name, insurance signal. I'm calling insurance signal. We have input and output pins. And if chip operates as we designed, input pin and output pin is enough to measure the performance. But sometimes the chip does not work. In such case, we want to investigate the chip performance of this block and this block and this block. Or we want to know why the chip does not operate. So we have to output the probing pins. In case we fail, we have some kind of mistake on the result. So we call that insurance signals. Of course, we have insurance input signals and insurance output signals. So how to measure the internal state if the circuit does not operate as we designed? So we have to brain simulation if this block does not work, what happens? And how, in such case, how to measure this block without this. And it is always a question that this insurance signal is enough or not. And most of the case, once we put insurance signals, that insurance signal, of course we want to measure the very important signals. So that important signal means it often causes noise if we probe. So insurance signals, the two questions, is that enough? And does it affect the noise? Or does it affect the overall circuit performance? We have to consider it. So you need very large experience to decide what kind of insurance you put. Maybe for beginners it is very difficult to decide what kind of insurance we need. So this is maybe advisors or the managers have to very much deeply consider what if this, what if this. And other things we have to consider the assembly. So first we decide the maximum operating frequency. So if the operating frequency is several gigahertz, we cannot put it on the package. So the package has parasitic inductance, and so maybe gigahertz signal does not come out from the package. So in such case, we use this kind of code. And how many pins we have? For this, the number of pins are very restricted. We have only 2 high-speed input and 2 high-speed output. And also this one has a lot, maybe this block has 7 pins. And maybe at most it has 15 pins. And if you have 15 pins, it is difficult to have the horizontal adjustment. Maybe 3 pins, it is easy to horizontal adjustment, but 15 pins, let's say 15 pins, it is difficult to adjust horizontal. So at less pins, it's easy for us to measure, but we sometimes want as many pins as possible. So how many pins it is for that point? And of course, how to measure this one or this one. And if you use this one, you cannot use all the pins by using this, because you have to do some kind of handcraft. So if you use all the pins, and the handcraft will be very difficult. So the pin assignment is also important. And measurement macro. What kind of measurement macro we want? The first thing is it's possible to measure with existing devices. I mean existing measurement devices. And for example, your signal generator have the output is only 3 gigahertz, but you want to have 5 gigahertz input flow. What to do? In such case, you have to develop your VCO by yourself and put your VCO so that only DC voltage will control the internal flow. And also, once you want to assemble the circuit into package, and the package frequency, the maximum frequency is 1 gigahertz, but you want 10 gigahertz operation. Also, you need to develop VCO by yourself and inputs that, and you can control the frequency by DC, and that is very easy for me. And in such case, when you measure, maybe you will use sampling oscilloscope. So you have to design a divider by yourself and output the divided flow. For example, divided by 128, you will output it and use it as a trigger for sampling oscilloscope. So in case you have to develop your measurement macro by yourself. The next thing, you will decide the pin distributions. So if you do a direct probing, pin distributions follows the pin pitch and number of paths your probe have. For example, in this case, our probe has 5 pins GS, GSD, and the path pitch is, in this case, our probe's path pitch is 100 micron. So I put 5 paths with 100 micron pitch, and we use these tools and high-speed signals and decrease our ground inside of the circuit. And this is the slow speed probers. So we can use, this is of course with power supply as well as a slow control signal. And so for the direct probing, the pin distributions are decided by what kind of probe you have. And then the other thing you have to consider is you have probes like here, and both probes should not interfere with each other. So from 2 directions it might be okay, but from 4 directions, the 2 probes sometimes interfere each other, and we cannot get it. So before deciding the pin distribution, you take much care how we probe and how to decide the pin distribution. Then we pay much care that the probe interference. And when we assemble in package, and you will have a board processing. So I often use the signal is sandwiched by 2 ground. GG, SGG, VGG, SGG, so that it is easy to work on. You have to put, sometimes you have to put chip capacitors, or sometimes you have to connect 50 ohm transmission lines. And also you have to consider the noise emission. So how many capacitors you have to put on the board, and important signals are sandwiched by ground, or you have to take into consideration the symmetry of the signal and signal. And again, the V and G should be side by side. And if you have multiple pins, VG is better than VG. And other thing is power and ground. You put the power rings for IOs. And the internal power and internal ground should be meshed with white metals. You don't make thin metals like this. And substrate noise. Substrate noise is the noise attacking a noise from digital to analog. And the one way to prevent substrate noise is using a deep end well. And for deep end well, we have a capacitance here so that the signal hard to get into the P inductions. But for high-speed signal, can get into that. So we have 2 ways to use deep end well. Deep end well around another portion, or deep end well around the noise generation. So around I/O have to drive the picofarad capacitance on R and anything. The wires in the inverters have femtofarad, and the capacitance on the pad is picofarad. And picofarad millihertz switching means large amount of current flows. That means large amount of noise is generated. So deep anywhere around I/O are also good. for prevent the substrate noise. And gathering. And gathering means we will put the ground connection around the anode part and bring it and guard so that the digital noise is going out. So however, the problem is the gathering itself has a reluctance, so high-speed signal does not work. So you have to estimate how to use Deepwell and how many pins are assigned for gathering. And of course, many pins you can reduce the inductance, so the noise can easily go into the ground. So how many pins are assigned for gathering and how many pins are assigned for power supply itself, and how many pins are assigned for ground, IO ground and IO power. Such kind of pin assignments are also. And block distributions. And for example, you have anode circuit and high-speed circuit. And if there is a anode circuit distributed along the chip, it might be difficult to protect them. So sensitive circuit wants to get into one place so that it is easy to protect them. So the analog or high-speed blocks are gathered in one place. That's easy to protect them. And internal wire, for example, from this is an input IO, and internal wire here tend to be long. And long wire means easy to have antenna error. And antenna error is also nightmare. And you will have antenna error at the final stage of your design. So you will have antenna error when before 1 day of the deadline. You will have nightmare on that stage. And so, after taking care of all of these things, and you pass LVS, PLC antenna name, then you can submit the data, and you can go out to have a drink. So this is antenna rule. So, and after submit your data, maybe you go out to have a drink, and next day, myself in yesterday is different person in today. So maybe when you submit your data and go out and spend 1 month and you get the real chip, you want to start measurement of the chips. But your design in your mind is already gone. So it takes time to remember what kind of point we have to take care of, what kind of insurance signal we put. All the data are gone after 1 month. So I recommend you to prepare for measurement from as soon as possible after submitting your data. So first, you might start a board design, or you start a handcraft to make how to put capacitors on power ground, something like that. And this is, for example, for my case, this is pin distribution. After deciding the pin distribution, we start to draw the whole layout. And we make the whole and put capacitance and put the transmission line and SMS connectors and prepare for everything for measurement. And also, we start writing a program for measurement. the measurement means program. Most of time in measurement, rule is placed to the computer and do a program and debug. And so write a program for measurement, and I recommend you to start writing a program after submission. And sometimes we have to write a pattern. And maybe while you design your circuit, you have a new idea. A new idea comes when you are involved into your design. So you will have some kind of patented technology, but you have a deadline for your design. So you finish your design and then you write. And okay, and measurement equals program. And sometimes we have good measurement result. But in the next days, we cannot see the same measurement. It often happens. So once you have a good measurement result, you have to record it today, now. So every encounter is a treasure. So once you have good measurement, you have to record it right now. The chip on yesterday is different on today. The person myself yesterday is different from the person myself today. And after measurement, you write a paper and submit to a conference. How many of you have write a paper and present at the conference? Maybe in the future, you write a paper. When you write a paper, first you decide the title of your paper. And the title is very important. So title is very important. So you can take 1 hour to think about the title. And after deciding a title, you will write an abstract, introduction, and conclusion. Not write how to design circuit and what is the measurement result first. That is the last. The first thing you have to write is abstract, introduction, and conclusion. And after that, you will prepare for the next design. And now you design your circuit by yourself and prepare for the measurement and measure the chip by yourself. So you are the best friend with that circuit. And you know every good point and bad point of the chip. So you can design the next generation, modified and improved version of your new circuit. So here you use your imagination and creativity and design better and the best circuit. And this is the last message. And from lesson 1 to lesson 10, you learned many things. Or maybe there are unknown things is becoming known things. Unknown are converted into known, hopefully. And incomprehensive things turns into comprehensive things, hopefully. And you feel uneasy when you use your CAD tool, but now you are use your CAD tool with confidence, and you are dependent. You ask your manager to tell me what is this and what is that, but now you know that, so you can be freedom. And before the lesson, you were my student. But now, you are my rival. Okay. As a designer, you are my rival now. Okay. And the semiconductor industry is very fair market. Very fair compared with other markets. So semiconductor industry is very fair, so you can be more free and more rich, and you can have more happy life by this field. Thank you very much. Huh? Yeah, more rich. More rich. You can file a patent, or yeah, I'm sure you can do this. Any questions? Okay. Okay, thank you very much.
This be very valuable slide and recommendations.
I'm sorry?
I get that it's very valuable recommendations. I get that he tell us about the experiment or more than the